Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the fourth lecture and we will be continuing with the overview of VLSI Design Flow. In the previous lecture, we had looked into system level design. We had discussed how the functionality at the system level is partitioned into hardware and software. Now, given a function that is implemented, that needs to be implemented in hardware, what are the next step? The next step is to basically make a specification out of for that given hardware and then taking it through the VLSI design flow, right? So we'll be discussing that part of the system level design in today's lecture. In particular, we'll be looking at how a functional description at the system level can be translated to the RTL. And then we'll be looking into the concept of reusing RTL and behavior synthesis. Now, once we have done the partitioning of system to hardware and software, we have take the hardware component and develop a functional specification for it. Now, this functional specification can be made at the in a high level language, for example, C, C++, or MATLAB. So, at a very high level language, we can make the specification. Why will we want to make a specification in high level language? Because there we have lots of flexibility and can do a lot of experimentation and analyze various trade-offs of the algorithms on the system behavior and other things. And therefore, we want to do an initial analysis or make a functional specification in a high level language where we have lots of flexibility. But there is a downside with this also. The downside is that once we make a specification in a high level language, we need to then take it to an RTL out of it, right? Or we need to convert that specification to an RTL, and that creates what is known as an implementation gap, right? So we write a functional specification in C, C++, System C, MATLAB, or it can be a metadata, and finally we need to convert it into an RTL, right, which is typically in Verilog, System Verilog, or VST, right? So now this conversion needs to be done, and that is what we mean by implementation gap is there, right? Now this is an important implementation gap. Why? Because when we describe a functionality in high level language, typically we do not have information of timing, meaning a given task needs to be performed in which clock cycles, right? But when we want to get an RTL out of it, we need to describe the design in terms of how the data flow from register to register at various instant or clock cycle. So an RTL carries a kind of timing information, or which operation of the function is being performed in which clock cycle, right? And we need to take important design decisions such as pipelining and resource allocation and those kind of things which needs to be there in the RTL, right? And this timing information is missing in the functional description or in a high level language, and therefore we need to fill that implementation gap. Now, how to fill that implementation gap, we'll see later. Before that, let's understand briefly that what an RTL is and how what is a structure of a general RTL. In this figure, we are showing the a general structure of an RTL. So RTL, in RTL, what we do is that we model the flow of data between registers, and therefore RTL can be also be called as data flow descriptions. It has got two distinct parts. One is data path and the control path. In the data path, what is done is that the major portion of computation is done. For example, there are ALUs or arithmetic logic units which is doing a kind of computation. These units can be adder, multipliers, or logical units, AND gate, OR gates, and those kind of logical operations will be performed in the data path. And how this data moves from moves, that is decided by a control signals which is generated in the control path. So the FSM generates this control signals which is on the control path, and MUX passes the data based on this control signals. And we have registers from which the information can go to the arithmetic logic units and so on. So this is the general structure of an RTL. An important point to note here is that in an RTL there can be computation which can be series. For example, if we consider this path, then the first ALU computes, then the second ALU computes, and so on. So this is a kind of serial computation. And there is there are some ALUs. For example, if we consider this ALU and the other one, right? So these two ALUs are performing computation in parallel, right? So in an RTL there can be processing which are done in serial, for example these two, right? And there can be processing of data which can be done in parallel, right? These two. So RTL needs to be modeled in a language or in a framework where both kind of modeling is allowed, that is the sequential modeling as well as concurrent modeling. And hardware description languages basically provide that facility, and therefore RTL is typically modeled using Verilog, VSDL or System Verilog languages. We have discussed that there is an implementation gap when we describe a design in terms of functional specification in high level language and the RTL and RTL, which is basically describing design in a way in which data moves from register to register. Now, how do we fill this implementation gap? There are typically three methods in which this implementation gap can be filled. The first one is, of course, the manual coding. Given an algorithm, we can code an RTL, right? Manually code an RTL and describe that which arithmetic operation or which kind of computation is done in which clock cycle, and add the timing information and other details in the RTL manually. That is one way of doing things. The other could be IP assembly, which is basically reusing an existing RTLs, right? This is typically used in SOC design methodologies. And then there is the third thing is using an automatic tool. So there are tools which are known as behavior synthesis tool, which can automatically generate an RTL for a given description of a design in high level language. So manual coding of a design in Verilog will be looking in later lectures. For now, let's look into this IP assembly method or reusing existing RTL method of filling the implementation gap, and also the behavior synthesis method. Now, reusing RTL is especially popular in SOC design methodology. Now, what is SOC? SOC is system on chip. So, what is a system on chip? A system on chip is a complete system built on a single chip. Earlier, what we used to have is that we used to have various components. For example, processor separate, memory separate, and various other components separate for a system, and we used to integrate them over a board, right? On a board, we used to connect and get the required functionality. But what happened is that with the increasing level of integration, now in a given chip, we can embed all those things together inside one chip, and that chip in which the various components are integrated together, that is known as system on chip or SOC. Now, what an SOC can consist of? It can consist of processors, hardware accelerators, memories, peripherals, analog components, and RF devices. These are the few examples, right? There can be many other things, and these things are basically connected using some structured communication links, right? And these SOCs can also contain embedded software within it. Now, what is the merit of SOC design methodology or SOCs? Is that it improves productivity. Why? Because what we do in SOC design methods is that we do not design individual components. We reuse the existing components. Reuse the existing components means that if we have already designed a processor, we take that processor and put it in our design, right? And then we take another memory component which was pre-designed, put in the SOC. So the designer's task is not now designing a complicated chip in which each individual components are designed, but only integrating those components, right? So the task of designing reduces to integrating various components together at the system level and of course verifying it, right? And this is a simpler task than designing each of the components at the individual level, right? And that is how we get a lot of or improved productivity in SOC based design. Then it also lowers the cost because we take less time to design and many things we reuse, right? So we do not spend much effort in already done things, right? And therefore it saves cost in designing. And it increases the features. Since we can easily integrate many things together, we can, on the same chip, we can have many features, which was earlier not possible, right? So the SOC design methodologies allows us to implement very complex features or complicated functionality within a single chip, right? So these are the merits of SOC design methodology, and therefore these days lot of design, a lot of industrial designs are designed using SOC design methodologies. Now, an integral part of SOC design methodology is intellectual properties or IPs, right? Now, what are IPs? IPs are pre-designed and pre-verified subsystems or block. For example, it may be a processor, or it can be a memory unit, or it can be peripherals or many other kind of things, right? Now these are already pre-designed. This pre-designing can be done either in-house by a company or a subsystem or an IP can be purchased from third-party IP vendors, right? So it can be developed internally or it can be purchased from the IP vendors. Now, what is the content of an intellectual property? It can be hardware blocks, for example, processor, memory, interface, or it can be software like real-time operating system, device drivers, and so on, right? So the content of IPs can be various depending on what the IP is. Even some IP can have verification component, right? That, for example, what is the communication protocol for a given IP and so on. So those things are basically there in already designed, verified, encapsulated in a format so that it can easily be instantiated in another design, and these verification IPs very much help in or eases the verification effort, right, or reduces the verification effort. Now while designing using IP method or SOC design method, an important concern or important aspect is how to share the information. Why this is important? Because typically the IP is made by another group or another company and it is taken from them and then put or integrated into another design, and the one who is actually designing or integrating the components, that designer may not have worked on that IP earlier and may not have the details of how to use it, right? So IPs contain information related to structure, configurability, interfaces of the system, and the challenge is how to package this information so that the IP integrator or who is using that IP in the SOC, he or she is able to understand that how to configure that IP, how to connect that IP, and so on, right? So this is a challenge because the person who is actually making the IP is a different, or the group who is making the IP is different, and the group who is using that IP is different. And this problem, it becomes more difficult because typically the standards are not followed, right? No uniform standards are not followed in this kind of package, right? And this is a challenging task, and the IP vendors one who is creating the IP, they must be careful about how they are sharing the information, and similarly the one who is using those IP must be careful of how they are using the IP in their designs, and they are not violating the assumptions that are made by the, say, IP vendors or the one who has designed the IP. Now integration, so now integration of IPs, or the how the SoC design is made, in that the major task for a designer is to basically instantiate various IPs, right, and then making a connections out of it, right? That is the major task, because we are assuming that IP is already there, it is already verified, it is already designed, verified, and it is available to us for using in our design. So as a designer of an SoC, the major task is to instantiate those IP and make the connections out of it. Now how to go about doing that? So to do those integration, what an IP integrator or or the one who is designing an SoC can do is that they can create metadata. So these are metadata are the top level IP models, bus interfaces, ports, registers, and the required configuration. Those needs to be filled in by the IP integrator, and there are some standards for filling that information, right? For example, there is IP exact, system RDL, XML, or even spreadsheet can be used for filling those information, those metadata, that what are the IP models that needs to be there in your design, how these what are the bus interfaces, what are the ports, what are the registers, and what is the configuration of each of the IPs. Now earlier this kind of integration used to be done manually, but those were error prone. Now there are generator tools which produce an SoC level RTL with the instantiated IP, rather than manually doing or integrating those or writing an RTL for the integration for those IPs. What we can do is that we can use a generator tool. The generator tool will read the metadata about which IP to use, how to connect, and other things, and automatically produce an RTL with the instantiated IP, right? A generator tool can also produce a verification environment and low level software drivers. So this can greatly help the designer and allow us to avoid mistakes in IP integration. Nevertheless, IPs can have or configuring IPs can be challenging, because IPs can have configuration parameters such as bus width, power modes, and communication protocols. So now when we are making or integrating an IP in our design, then what to choose for the bus width, what to choose for power models, and so on. So their IP assembly involves choosing the set of configuration parameters, and this task is challenging because there can be too many parameters and simply too many combinations of parameters that can be chosen. Out of them, which one is optimum? That is a difficult question to figure out, right? And the other problem is that there can be inconsistency between different IPs. For example, if we choose IP 1, the width as say 8, and other as 16, it may be incompatible for communication or something, right? So when different IPs are interacting with each other, the configuration should also be consistent, right? That is another thing that we must ensure or check while doing assembly, IP assembly. Another thing is that how do we connect different IPs? Earlier what we used to do is used to connect different IPs using ad hoc bus based connection, right? It was okay till the time the connections were not very complex, right? But with these modern SOCs, what is happening is that the level of complications between the connections between IPs, that has increased tremendously, and as such the ad hoc method of manually connecting or making bus based connection, those do not work. And now what we do is that we follow a structured network approach, which we borrow from, say, computer networks theory and apply it in VLSI. And these structured network inside SOC are known as network on chip or NOC. And another challenge of integration of IPs is verification, right? See, when IPs are already there and we have integrated it, integration is a simpler task, right? But once we have integrated it, after integration we need to also verify that we are getting the required functionality, right? And this has to be done, and this verification needs to be done throughout our design or to the entire design. And this verification is a difficult task because there is a huge functional space, right, over we need to verify, right? There are too many configuration parameters and many modes of the circuits or the IPs that it can work and so on. And then we have to verify that under all conditions in which our IPs can work, we are getting the required functionality, and therefore this is a challenging task. Added to that, if we consider that we need to also test verify that the hardware portion of SOC is working correctly with the software portion also, then our verification challenges becomes more, right? So these are some of the challenges that we need to consider while doing SOC design, right? Now, the other way in which we can convert functionality in high level language to an RTL is behavior synthesis. Now, in behavior synthesis, what we do is that first let's look into what is behavior synthesis. So behavior synthesis is the process of converting an algorithm which is not timed, meaning it doesn't carry the timing information, meaning which operation needs to be performed in which clock cycle, that information is not there, to an equivalent RTL design in RTL which is fully timed, meaning that it is saying that how the computation is done in which clock cycle and so on, right? And while doing this transformation, it must satisfy the specified constraints of resource uses, latency and other things that we'll see, right? So the framework of behavior synthesis is shown in this figure. We give to the behavior synthesis tool the given algorithm, which may be in C, C++, System C or MATLAB, and then we also give the constraints of resource uses, frequency, latency, power, and the library of resources, meaning that if we have adder, multipliers and other entities in our design, if the behavior synthesis tool uses them, then what will be the cost implications of each of these entities? Those will be contained in the library of resources. And at the end, what the behavior synthesis will give us, it will give us an RTL model, which will be typically in Verilog or VSTL. So behavior synthesis is also called high level synthesis. Now, what are the cost metrics that needs to be considered in behavior synthesis? An untimed algorithm can be implemented in many ways. So for behavior synthesis tool, there is lot of options because there are a lot of design decisions it needs to make, right? Because there are lots of possibilities in which it can, a given algorithm can be implemented. Now, out of those implementation, which one is better, which one is worse? To do those kind of analysis, the behavior synthesis tool needs to evaluate the cost of each of the implementation and pick the one with the lowest cost. So what are those cost metrics? So the first one is, of course, with the easiest one is the area, right? It can be measured simply by the number of circuit elements, right? Number of circuit elements in the RTL as that will be used, and that can give us the kind of area measure for the RTL generated by the tool. Now at a broad level, we can ignore the area of the wires and we can just consider the area of the elements, logic elements, arithmetic units and registers and so on, right. So and then the second cost matrix can be latency. What is latency? It is the number of clock cycles required before results are available, right. So if we make a change in the input at input, then after how many clock cycles that result is available at the output, that we call it as the latency, right. And then the third important thing is at what maximum clock frequency a circuit or a design can operate, right, or it can be measured using worst case combinational delay. So this requires a little more understanding of the timing. So we'll be discussing in the next slide. And what could be the other cost measure? The other cost measures could be power dissipation, throughput, and there could be many other considerations that behavior synthesis tool can account for while generating a solution. Now let us understand that what is the maximum clock frequency, or how the maximum clock frequency can be estimated for a given design, right. So to get a full understanding of this, we need to go into the static timing analysis, which we will be doing later in this course. But we can get a crude estimate that on what factors maximum clock frequency of a synchronous circuit will depend. So in this course, we'll be mostly looking at synchronous circuit. So let's first assume that there is a synchronous circuit, and for that we define we look into a few definitions, and then we'll be looking into how the maximum clock frequency can be determined. So in the synchronous circuit, we define what is a path, right. So the path is a sequence of pins through which a signal can propagate. For example, if you have an AND gate, then an inverter, then a NAND gate, and so on. So the sequence of pin will be 1, 2, 3, 4, 5, 6. So these are sequence of pins. So these sequence of pins form a path. Sequence of pins through which a signal can propagate, that is a path in a combinational circuit. Now what is a combinational path? Okay, so before explaining combinational path, let me explain difference between what is difference between a combinational circuit element and a sequential circuit element. Combinational circuit elements are those circuit elements whose output depends on the current inputs only, right. For example, AND gate, OR gate, XOR, right. So these kind of, or multiplexer, decoder, this kind of circuit elements are combinational circuit elements, because whenever we make any change to the input, the output we can change, right. Then there are sequential circuit elements in which the output depends not only on the current input but past sequences of inputs. For example, for flip-flops or latches, the output will depend on the past value that it got at the D pin or whenever the clock came last, right, and so on. So the combinational circuit elements are AND gate and those circuit elements, and sequential circuit elements are flip-flops and latches. Now what is a combinational path? A path that does not contain any sequential circuit element, such as flip-flop. So if there is a flip-flop, right, then we cannot cross it, right. So the path is starting from here and it is ending till here. So a combinational path is a path that does not contain any sequential circuit element such as flip-flop. So flip-flops cannot come in a flip-flops and latches, or any other sequential circuit elements cannot come in a combinational path, meaning that only combinational circuit elements, for example AND gate, OR gate, or those kind of combinational circuit elements, if those exist in a path, then we say that it is a combinational path. Then there is a concept of sequentially adjacent flip-flops. Now if the output of one flip-flop is fed as an input to the other flip-flop through a combinational path only, then we say that it is a sequentially adjacent flip-flop. For example, consider this flip-flop. The Q output, the output from this Q pin goes to this D pin through the combinational logic only. So this pink cloud that is shown here, that is consisting of only combinational circuit elements, right? And therefore any path from this Q pin to D pin will pass through a combinational path only, and therefore if the output of one flip flop, in this case Q pin, is fed as an input to the other flip flop through a combinational path, then we say that these two flip flops are sequentially adjacent. The one which is launching the data, that is known as launch flip flop, and the one which is capturing the data is known as the capture flip flop. So this is the capture flip flop and this is the launch flip flop. Now in a synchronous circuit, data launched must be captured by the sequentially adjacent flip flop in the next clock cycle. In a synchronous circuit, what happens is that the data that is launched at a particular clock cycle, that should reach the D pin of the sequentially adjacent flip flop by the next clock cycle, right, or next clock edge, right. So so in a synchronous circuit, data launched must be captured by the sequentially adjacent flip flop in the next clock cycle. So the maximum time that is allowed for the data to move from this Q pin to D pin is basically 1 clock period, right. So we can write that the clock period should be greater than the delay of the critical path Tp, where is greater than D max. What is D max? D max is basically representing the maximum delay that is there between Q and D. Note that between Q and D there can be multiple paths. There can be multiple paths. Out of this path, the one which is exhibiting the maximum delay, that is D max. So what for a synchronous operation, we want that by the time the next clock edge comes here, the data should start from here and reach the D pin, right. And therefore we have the constraint that Tp, that is the clock period, should be more than the D max or the maximum delay that is there in the on the data path, right. And the clock frequency is the reciprocal of the time period, and therefore F max will be less than 1 by D max. And therefore we can say that the path that is deciding the clock frequency is the combinational path that has the largest delay, right. The one that is having the largest delay, that will be determining the maximum clock frequency at which a circuit can operate, a synchronous circuit can operate, because if we increase the clock frequency more, then the clock edge will reach very early at the capture flip flop, and the data will not be captured synchronously at the capture flip flop. So this is just an approximate description of that how the maximum clock frequency for a circuit can be calculated, but the detail of these calculations we will be looking at in later course of later lectures of this course when we discuss static timing analysis. Now let us take an illustration of behavior synthesis, how behavior synthesis is done. So suppose we are given an algorithmic description y is equal to a plus b plus c. Now this is an algorithmic description. There is no description about when the plus operation is carried, when the another plus operations is being carried out. Now for this, it can be implemented in many ways, and the cost matrix we can consider is a latency, the area or the circuit elements that are used in the circuit, and the maximum delay of the combinational path, right. So one of the implementation can be, we have two adders, a plus b is be performed by a1, then the result is going to the next adder, and we are getting the result which is going to the D flip flop, and whenever the clock edge comes, the result is available at y, right. And for this implementation, we can compute the cost as resource uses as two adders, right, and one register, and the latency is 1 clock cycle, because if we make one change at the input, the output will be available in the next clock cycle, right. That change will be available in next clock cycle. So latency is 1 clock cycle in this case, and worst case delay or the longest combinational path delay will be, say, this path in which you have 2 adder delay, right. Now there can be another implementation in which we added a flip-flop in the middle. Now, as a result of that, what changes can happen? First of all, area increases, one flip-flop or one area of one register increases. Then the latency increases to 2 clock cycle. Why? Because if you make change in A, then the effect on Y will be after 2 clock cycle, right? Because 2 flip-flops are there, and therefore latency increases from 1 clock cycle to 2 clock cycle. But what happens to the worst case delay or the longest path delay? So the longest path delay can be this one or this one, right? There is only one adder in the only one adder or one between sequentially adjacent flip-flops or from input to the flip-flops. So in this case, worst case delay is one adder. So in the earlier case, it was the delay of the worst case delay was delay of 2 adders. Now we have in this case we have the delay of only one adder, and therefore this circuit can operate at a higher clock frequency. Why? Because we saw that f is less than 1 by d max. Now in this case, d max is related to only one adder compared to 2 adder, and therefore f will be greater for the second case. Okay. Now let's look into another implementation of the same thing in which we have used only one adder. Okay. Now this adder is being used to compute A plus B in one clock cycle. So A comes and B comes whenever the select line is 0. Whenever select is equal to 0, then A and B comes, it is added and you get the result as A plus B. Whenever clock comes, the output is A plus B, right? And this is fed to this, right? A plus B. And whenever next clock edge comes, next clock edge comes, what happens is that since Q is connected to D through an inverter, this Q will toggle every clock cycle, right? So in one clock cycle it will be 0, then in next clock cycle it will be 1, then 0 and 1 and so on. So in the next clock cycle, what will happen is that this select signal will take a value of 1, right? So when 1 is taken, the multiplexers, the 1 lines are selected, and in that case, what operation is performed by the adder? It is A plus B plus C, right? So in the next clock cycle, we'll have A plus B plus C. Right. So adder is used in the first cycle to compute A plus B and is used in the next cycle to compute A plus B plus C, right? That is C plus Y, right? So inputs to the adders are controlled by multiplexers. Multiplexers get select signals from the control circuitry. So what is the benefit of this implementation? The benefit is clear that we are using only one adder, right? Now for typically what happens that adders, multipliers and these kind of arithmetic units are more costly in terms of area, in power and other things, right? So if we reduce the count of these arithmetic units, we can save on area, right? And but what is the downside? Now we'll have the latency of 2 clock cycle, right? In one clock edge it is producing A plus B, and in the next it is producing A plus B plus C, right? So every 2 clock cycle it is producing the result, right? So the latency will be 2 clock cycle, and also the throughput, that is how many computation is done in 1 clock cycle, that is also reduced in this case. But what benefit we are getting? The benefit is in terms of area and possibly in the terms of power also. And what is the worst case delay in this case? It is adder plus multiplexer, right? So the whichever is the longest path, possibly this will be the longest path, right? Or maybe this one, or similar kind of other paths. So one of these paths will be the critical path, or the one which will be deciding the clock frequency. Now if we assign area and delay to these circuit elements, then we can easily compute the cost of each of these implementations. For example, for the implementation RTL1 or this part, we can say that the total area is area of A1 two adders, that is 200 plus 200 is 400 plus 1 register, that is 12, that is 412. Similarly, we can compute the area for other implementations. We can compute the latency and we can compute the delay for each circuit, each implementation. And then what the behavior synthesis tool will do is that these are three kinds of timed implementation for the algorithmic description y is equal to a plus b plus c. Now there can be other implementations also. We have not considered all of them, only three we have chosen for the illustrative purposes. Now out of this, behavior synthesis tool will choose the best possible implementation satisfying the constraints. Now what would be the best one? It will depend on the constraint or what objectives we have, what kind of design we want to implement. For example, if we want that area is to be minimized, right? So in that case, the tool will choose the RTL3, the third implementation, right, in which the area is minimized. But then the downside will be, of course, the throughput and the latency. Then if we want to minimize the latency, then probably we'll use the first implementation or RTL1. And if we want to maximize the clock frequency, then probably we can choose the RTL2, which has got the minimum delay, right? So depending on objectives, the behavior synthesis tool can produce one of these outputs among all the evaluated outputs. Now what are the merits of behavior synthesis? So the merits of behavior synthesis is that it allows automatic exploration of different possible implementations. For example, for a human designer, it may not be that easy to think of all three implementations. At least the third implementation was a bit non-trivial, right? And therefore those kind of implementation is difficult for a human to come up with, right? So the solutions that will be produced by behavior synthesis tool, those will be after more exhaustive search of the design space than the handwritten RTL. It reduces the design effort because it is done by an automatic tool, and it has got less chance of introducing errors compared to handwritten RTL. So these are benefits of behavior synthesis. And what are the challenges or demerits of this? The first is related to physical design, right? During system level design, the tool is not knowing much about the implementation over the layout and other details, and as such some solution can be produced which can later be found to be bad in terms of physical design or so. For example, the behavior synthesis tool can share a resource too much, right? So lot of signals come to a shared resource, and as such around that shared resource there can be a congestion, right? And that congestion will be found only during physical design. So the solution that may be produced by behavior synthesis tool, those may actually lead to some problem down the design flow because of the incomplete information it has, right? The other is the lack of readability, right? So the machine generated RTL code of or after behavior synthesis, those are really not difficult, not easy for human to read and understand. So if we want to make incremental changes or make some debugging in those RTL that is generated by the machine or that is generated by behavior synthesis tool, it is really difficult, right? So that is a big demerit. Another problem is that if we make small changes in the behavior, in the algorithmic behavior, the RTL can change widely, right? It will not the small change in algorithm can lead to a very big change in the generated RTL, and therefore making small adjustment to the algorithm and other things becomes really difficult with behavior synthesis tool. And there are verification challenges ensuring that the algorithmic description and the RTL are both actually matching in terms of functionality. That is again a difficult challenge that needs to be tackled by tackled by the designer who is using the behavior synthesis tool. So these are some of the important references that we have that you can look into for more details on the topics that I covered in this lecture. So in this lecture, we have looked into that from a given function, how we can get an RT, right? So this completes the first part of overview of VLSI design flow, in which we have looked into the system level design, right? So we have just took some or discussed very briefly what system design is, right? And then in the next lectures, while we will be looking into the flow from RTL to GDS, right? That is the main topic that we'll be discussing in this course. But first, we'll be looking into an overview of RTL to GDS flow in the next lecture. So that's it for this lecture. Thank you very much.